Okay guys, so today we're talking about dipoles, and in this little lesson you're just going to pause whenever you need to take the notes that are on the screen, and then of course play to listen to my explanations and see the examples. Write down as much as you want to in terms of the examples. So again, pause at any point. I'm just going to start talking. So what a dipole is that even though electrons are shared when atoms bond, they're not actually shared equally usually. So for example, if I have a molecule like carbon monoxide, I would draw the Lewis structure for that with a triple bond, and I would say that these 6 electrons here in this triple bond are being shared between the carbon and the oxygen. But the thing about it is they're not actually totally shared. And the reason for that is if we look at the electronegativity of oxygen, which if you remember from the last unit, electronegativity is pull on shared electrons. If you look at that for oxygen, it's 3.5, whereas carbon is only 2.5. And if you go back and look at your table of electronegativities from your Lewis structures notes, or further back in your notes, you can see that. So there they are. There's oxygen. There's carbon. There's oxygen, 2.5 and 3.5. So there's a significant difference in their electronegativity. And so because of this difference, we would say that the electrons shift more towards the oxygen end of the bond. They spend more of their time at this end of the bond than at the carbon end. And so that arrow that I just drew to show which end of the bond the electrons shift toward is actually a dipole. The only thing that we have to add to it that you'll see drawn on dipoles is kind of like a little plus sign at the tail of it, and that's what basically makes that arrow into a dipole. So again, the arrow points in the direction of the greater electronegativity. So let's try another molecule. Let's try NH3. So that's the Lewis structure for NH3. It is a pyramidal molecule, or trigonal pyramidal molecule. And if I look at the electronegativities for nitrogen and hydrogen, again, nitrogen 3.0, hydrogen 2.1. So the dipoles are going to be pointing towards nitrogen because it has a greater electronegativity than hydrogen. And that's true not only there on that first bond on the left, but it's true on all of them, because all 3 of those bonds are essentially the same thing. They're just a nitrogen bonded to a hydrogen, and the nitrogen has a greater electronegativity, so the dipole goes in that direction. And what that means is the nitrogen end of the molecule is slightly more negative because the electrons are shifting that way. They're shifting towards the nitrogen and away from the hydrogen. And that's going to have a lot to do with the properties of a molecule like NH3 that we're going to talk about next week. So let's try another one and see if you can figure it out. I'm just going to put the molecule on the page and see if you can draw the dipoles. We're going to go with CO2. Okay, so go ahead and pause it. See if you can figure out where the dipoles would be. Okay, so if you did it correctly, you should have again been looking at carbon and oxygen. Oxygen is once again bigger in electronegativity, so you should have a dipole going out towards oxygen there and out towards oxygen there. So those are the 2 dipoles that you would draw for this molecule. Now, this is a great example of a molecule that has multiple dipoles. And so because this molecule has multiple dipoles, I'm just going to pull this guy down here to talk about it a little bit. Because this molecule has multiple dipoles, what is that going to mean about the molecule overall? Well, we can make this statement. In molecules with more than one polar bond, and I guess I should stop and clarify. When I say polar bond, a polar bond is any bond that has a dipole. So this double bond right here between carbon and oxygen is a polar bond. And polar just means having opposite sides. And so if it has a negative side, which would be the oxygen end of the bond, and a more positive side, which would be the carbon end of the bond, it's a polar bond. A nonpolar bond would just be like, for example, a nitrogen bond to another nitrogen. Because it's two identical atoms, of course they have the same electronegativity, so there's no dipole to draw. So that would be a nonpolar bond. But getting back to my statement here, in molecules that have more than one polar bond, like CO2, the dipoles may add up or cancel out. And so, like for example, if we look at CO2, I've got two dipoles, and those dipoles are heading in opposite direction. I've got directions. I've got one going east and one going west, or one going to the right and one going to the left. And when those forces are pulling in opposite directions, they cancel each other out like a tug of war between two equally strong opponents. The rope doesn't move because the forces are canceled. They're opposing each other. And so that happens with CO2. But on the other hand, if you have multiple dipoles that maybe head in the same direction, you could have a situation like, for example, with water. So water, we get dipoles. And again, I'm going to consult my little table up here. I've got hydrogen and I've got oxygen. And so oxygen, you can see, is greater, 3.5. Hydrogen's only 2.1. So I'm going to put my dipoles going which way? Go ahead and pause it and see if you can figure it out. Okay, so they're going to go towards oxygen. And the dipoles should always be drawn parallel to the bonds. It doesn't matter whether they're above or below. You know, you could draw them down here. But it doesn't matter if they're above or below the bond. They just need to be parallel to the bond. All right, so I have one going up and to the right, and one going up and to the left. And because of that, what I would say is the overall dipole is the result of both of them together. So if I have one dipole that's kind of going this way and one that's going that way, the overall dipole is straight up. In other words, the molecular dipole, we call this, is the result of adding up those two individual bond dipoles. So this is referred to as the molecular dipole. Okay. Another way to do this that might work a little bit better for some people if they're having trouble understanding how I just added those two up. If I walk a block northeast and then I walk about the same distance northwest, where am I from where I started? Well, here's where I am now. Here's where I started. I basically went north, right? So that's all I did. I took those two dipoles kind of off to the side and I added them up, all right? The opposite would be true if I said, with this carbon dioxide, if I walk a block east and then turn around and walk a block west, well, there's no overall change in where I'm at. I'm back where I started. So that's why we say that there's no molecular dipole for carbon dioxide, okay? So let's try this. You're going to be asked to do this in just a few minutes on a little assignment in class. So we're going to do these first three as examples. So see if you can draw the Lewis structure for each one, and then see if you can put in the dipoles, and then see if you can decide if the dipoles cancel or not. And if they don't cancel, which direction do they go? So give them a shot. Okay, this first one I have NO2 1 minus. This is nitrite. And that 1 minus charge means that I have an extra electron to work with. So nitrogen has 5, Each oxygen has 6, so 2 times 6 is 12, plus that 1 extra electron, so 5 plus 12 plus 1 gives me 18, right? So I've used 4 just to connect my my 3 atoms, and I've got 18 left, so I'm going to go around and put them on my oxygens, and I find that I come up too short on nitrogen. And so what I have to do is a little bit more sharing. All right. And here's the problem, though. When I do that and I end up with a lone pair on my central atom, I have to recognize that this thing is bent. And I have to actually redraw it bent. So I'm going to redraw it to show that that lone pair on that central atom is going to bend the bonds away. And I'm going to show you why that's so important in just a second. So if I draw the dipoles now, they're not going to cancel completely because I have one that's going down and to the left and one that's going down and to the right. And so the overall result is just down. That's my molecular dipole. If I left it looking linear like my original one, then it would look like they cancel. So I don't want to leave it linear like that. As soon as I realize that it's bent, I need to redraw it bent. Okay. The next one, CH4, this one's a little bit easier. We've got just 4 hydrogens around our central carbon. All of our dipoles are going in towards carbon. And so you should notice that we have one going to the right and one going to the left, and those would cancel each other because they're going to oppose each other. And then one going down and one going up, and they're going to cancel each other. So I would say there is no molecular dipole, or I can simply say it's a nonpolar molecule. The last one, CH2O, I would put the carbon in the middle. I would put an O and 2 H's coming off of that. And I have, let's see here, 6, count this out here, 6 plus 4 plus 1 plus 1. So that's going to be, it's going to be 12 electrons to work with. Right now I've only used 6. Hydrogen's happy, so I'm going to leave that alone. So there's another 6. The problem is carbon's not happy because carbon only has 6. So I'm going to go ahead and erase a lone pair on my oxygen, and instead I'm going to double bond. Now this one is a lot like the first one that we did. You have to recognize this time there's no lone pair in the central atom. So I don't want to leave it in this shape. You have to recognize the shape. This particular shape is trigonal planar because all of the atoms are, there's no lone pair. There's no lone pair on that central atom. So rather than having a 180-degree bond angle and then 2 90-degree bond angles, if you look back at your notes on molecular shapes, you would see that this is trigonal planar. And so those bond angles are going to be more like 120 degrees. Now when I put in my dipoles, we're going to go from hydrogen towards carbon, and then from carbon towards oxygen. And I have up and to the right, up and to the left. The result of that would just be up. And then I have another up on top of that. So my overall molecular dipole is just going to be one arrow going up. So after you've watched this, you can rewatch it, of course, as much as you need to. And you can work together a little bit. If you have some questions, ask the folks around you. And then if you'll ask for the next sheet or for the assignment after the notes, and go ahead and give it a shot. We've got several problems just like the 3 that you see right here. And again, if you want to leave the computer out or use your phone or whatever you need to do to rewatch this as you're working through that assignment, feel free to do that.